Today I'm going to talk about Zener diodes. Now before we talk about Zener diodes, you have to make sure you understand diodes in general, so you can see the link to the videos and the reading material down below and up here. And let's move on to the Zener diode. So let me make a demonstration circuit to demonstrate what a Zener diode does. So we have a battery, a resistor, and a Zener diode. Now I've put the Zener diode in such that we have our positive and negative. Conventional current is flowing that direction, so we get positive on the cathode and negative on the anode. So this Zener diode is reverse biased because that's where we are interested in what Zener diodes do. When we forward bias a Zener diode, it acts just like a regular diode. So everything that you know about diodes forward biased, Zener diode does the same thing, nothing remarkable. But when they're reverse biased, they have a special characteristic. Now any diode is going to have a voltage when it's reverse biased, as you should know. When you reverse bias a diode, it doesn't conduct electricity. It acts like an open switch. But there gets to be a voltage for every diode. It's called the peak inverse voltage, where it breaks down and starts to conduct. And unless you really limit the current, it's probably going to destroy the diode. But a Zener diode is made so that it breaks down at a much lower voltage than most diodes, and it's constructed in a way that it's supposed to operate in that particular mode. So we're going to reverse bias the diode and see how it acts when it's reverse biased. Let's get some of this clutter out of the way here. I'm going to tell you about the little green man model of a Zener diode. So a Zener diode is a little box, and here comes one lead in. This is going to be the, I'll just draw little things here because I can. There's the cathode, there's the anode, and it splits off to a variable resistor and a voltmeter. And inside there is a little green man. He has his hand on that variable resistor, but he doesn't care what it is because he's interested in the voltage. So he's watching that voltmeter. And his job is to keep that voltage at a certain voltage depending on the rating of the Zener diode. Let's say this is a 7-volt Zener diode. So you buy a Zener diode, you specify 7 volts, and that's the voltage where it's going to break down and go into its operating region where we're interested in how the diode works. And so he has a little placard on the wall that says 7 volts to remind him that he wants to adjust this resistor to whatever it takes to keep 7 volts across it. If the voltage is low, what's he going to do? Well, all things being equal, let's erase our little guy here so we can draw a resistor. And all things being equal, let's put a current source here, and let's say that's a 1 amp current source. And we'll make this a 1 ohm resistor. So this will keep the current equal, and let's see what happens if we make changes. So if we have 1 amp going through 1 ohm, if you have current going through resistance, you get a voltage difference. Higher voltage where the current enters, lower voltage where the conventional current exits. So conventional current, notice our current source shows the direction of conventional current. And if we have 1 amp and 1 ohm, how much voltage are we going to get? Well, Ohm's law says you multiply to get your voltage, so we're going to have 1 volt. Now, we're going to keep the current constant, and we're going to increase that resistance to 2 ohms. So what happens? 1 amp times 2 ohms gives us 2 volts. So if the resistance goes up, we get a higher voltage typically, all things being equal. Or if it goes low, let's say it's 0.5 ohms, we're going to get 0.5 volts. So higher resistance leads to higher voltage, lower resistance leads to lower voltage. So the little green man inside this Zener diode has that variable resistor, and if he sees that the voltage across it is too low, he's going to crank it up and crank it up and crank it up until he sees that voltage right. And that's why we have this resistor here. People will say that this is a current limiting resistor, and yeah, it does limit the current. But you'll see it's necessary because otherwise you can't get a voltage across the Zener diode other than the battery voltage, not counting for internal resistance. But essentially, whatever voltage the battery has is what's going to be across the Zener diode. And when it gets to its operating region, it's just going to cascade out and burn up. And so we need something here. And like I say, people will say it's a current limiting resistor, and yes, it does do that. But also it makes it so that the voltage here can be different from the voltage here, because we have Kirchhoff's voltage law. This voltage plus that voltage must add up to that voltage. Well, if this is not here, then this voltage must add up to that voltage. So the Zener diode will not be able to do anything without this series resistor to make it so that this voltage does not have to be that voltage. So this voltage plus that voltage will equal that, and we'll see how that works. So this is going to be a variable battery. Let's say it goes from 0 to 20 volts. And let's get started. So I'm going to put a voltmeter across our Zener diode so we can monitor the voltage as well as the little green man inside it. So there it is. And we're going to put this at 0 volts. So what do we expect to see? Well, when it's reverse biased, any diode, including Zener diodes, is going to not conduct. And so it's going to look like an open circuit. So there's basically what we have when we're reverse biased. An open circuit. I'm going to detach that jar just to remind us that the voltmeter is not a current path. Remember, your voltmeters have very, very high impedance. A perfect voltmeter would have infinite impedance and would be an open circuit. So this does not constitute a connection between here and here. So we just have an open circuit. And if you review the material on open circuits, which I have linked below, you will see that if we have an open circuit, there's no current. So how much voltage are we going to have across this resistor? To have voltage there, we must have resistance plus current. There is no current. So the voltage difference is 0, meaning that the voltage here is the same as the voltage here. There is 0 difference. So with this being an open circuit, I can crank this to whatever voltage I want, and I'm going to see that voltage here because there's no current. So don't forget, we may have resistance, but with no current, we have no voltage difference. And so whatever voltage we see here is the voltage we see here. So with an open circuit, the voltage across that open part of the circuit will always be equal to the source voltage. So I crank that up to 20 volts, I'll see 20 volts here. Except we do have a Zener diode there. So let's see what that does. So the little green man in there has his variable resistor, and he's watching it, and he sees us changing the voltage. Let's go ahead and put this up to 1 volt. So what's going to happen? Well, the Zener diode is still going to be pretty much an open circuit because he wants to see 7 volts here. So don't forget, that's his instruction, 7 volts. What's he going to do? He's going to crank that variable resistor to its highest possible resistance, which is basically an open circuit. So we still have no current flow. This still looks like an open circuit. So no current flow. We start with 1 volt. We still have 1 volt left over. This is going to be 1 volt. And the little green man says, sorry, boss, I can't give you what you don't give me first. I can only give you 1 volt. Let's crank it up to 2 volts. Is that going to change anything? Well, this is going to go up to 2 volts. So the little green man sees his voltmeter go up to 2 volts, so he's going to crank his resistance as high as it'll go, trying to get it up to 7 volts. He's not going to be able to do it. Sorry, boss, that's all I can give you. So that continues all the way up to its rated voltage. So let's put this at 7 volts. So what's going to happen? Zener diode is still reverse biased. It's still non-conducting, still looks like an open circuit. There's still no current. And so we start with 7 volts. We have 7 volts here. Don't lose anything because there's no current, so there's no voltage difference. 7 volts, 7 volts. We still see 7 volts across the open part of the circuit. But the little green man is happy now. He says, there's your 7 volts. Got it. But what has happened to the Zener diode? Really basically nothing. He still has that resistance cranked up as high as it'll go now to get that 7 volts. So let's change this to 7.1 volts. Now what's going to happen? our voltage across the Zener diode is going to go to 7.1 volts. And the little green man's going to see that. Now what's he going to do? He needs to bring that voltage down, so he's going to crank his resistance down. So the resistance is going to drop until this is 7 volts. What's that do here? Well, Kirchhoff's voltage law says that the voltage across our components must add up to the source voltage. So if we have 7 volts here and 7.1 volts here, we must have our other tenth of a volt right here. So now everything adds up. 7 volts, 0.1 volts, adds up to 7.1 volts. How does that work out? Remember that the little green man is adjusting his resistance to whatever it takes to balance out. What's this resistor here? Well, we don't know yet. We just have to make sure that that resistor is big enough that it limits the current such that the Zener diode does not exceed its power rating. So let's take a look at our diode specification here. Let's say it's 7 volts at 50 milliamps. That's probably within 10 or 20 milliamps of what the real current would be for a typical small Zener diode. And let's make that a 1 watt diode, which is a typical wattage for a small Zener diode. They do make Zener diodes with much higher wattages, but typically we just use 1 watt Zener diodes because usually we don't need to be delivering a lot of power with them. So 7 volts, 1 watt, 50 milliamps. So what that means is we want to set this resistor such that with our nominal voltage over here, we have 50 milliamps going through that diode, because it's rated at 7 volts at 50 milliamps, which means that if we go above 50 milliamps, that's going to go something above 7 volts. Not much, because the Zener diode is going to be very close to what it's rated at. But he can't be perfect. So if we go above 50 milliamps, this might go to 7.1 volts. Go higher, it might go to 7.2 volts. Or if we go below 50 milliamps, it might go to 6.9 or 6.8, or maybe even closer to the 7 volts. But it's not going to be absolutely perfect, but it's going to be pretty close. But we want to design it so that nominally, meaning that whatever our nominal voltage is here, we're going to have 50 milliamps going through the diode. So let's look at that resistance a little later. Let's not worry about what it is now, but assuming that the resistance is such that our current is limited, such that we do not exceed our 1 watt on the diode, everything's going to work. So now, once again, I put this at 7.1 volts. This goes up to 7.1 volts. The little green man sees the voltage go high, so he cranks his resistance down until he sees 7 volts. And so then we're going to have 7 volts here, 0.1 volts there, adding up to 7.1 volts. Now let's go up to 8 volts. Now what's going to happen? This is going to go up above 7 volts. Little green man is going to crank his resistance down until it's 7 volts. And once again, that's going to balance out the circuit so that we have 7 volts here. 7 plus this must add up to 8. So we'll simply have 1 volt across our resistor. And if we crank this up to 10 volts, this is going to go up. Little green man cranks his voltage down until it balances out. 7 volts plus watt equals 10. Now we will have 3 volts across our resistor. Now let's say that this is the nominal voltage. We expect this voltage here to usually be 10 volts. We will usually have Zener diodes in places where we expect voltage fluctuations, where we need to have a steady reference. So there's our steady reference at 7 volts. This is nominally 10 volts, but might go up or might go down. That's why we have the Zener diode in there, because we need that somewhere else. But nominal voltage 10 volts, so we expect to see 7 volts here and 3 volts there. So what resistor will we put here? Well, we simply need to make a resistor that will have 50 milliamps when there's 3 volts across it. So we'll draw a current arrow there, 50 milliamps. So what resistance would that be? Well, if you know your voltage, you divide into it. So we know we want 50 milliamps, we have 3 volts, so the resistor will be 3 divided by 0.05 equals, and that comes out to be a 60 ohm resistor. I'll put that in blue just to make it stand out. 60 ohms. So that's what we would do in that case. If that was the nominal voltage and that was a 50 milliamp Zener diode. And so there we have our 50 milliamps, we get our nominal 7 volts, and there's our circuit the way we want it. So that's in a nutshell what a Zener diode does. It is simply a variable resistor that adjusts itself to whatever resistance it takes to keep the voltage across it at the rated voltage. And it will do that as long as it has the voltage to start with to work with. So if this voltage is below the rated voltage, the voltage across the Zener diode will equal the battery voltage because it now acts like an open circuit. But as soon as the source voltage exceeds the rated voltage, then the Zener diode is going to crank its resistance down to whatever it takes, or up if this happens to go, if this voltage goes up, it'll crank its voltage down. If this voltage goes down, it'll crank its voltage up to whatever it takes to maintain that voltage. And of course, whatever voltage is not here gets dumped across the series resistor over here. So if we crank this up to 11 volts, we're going to get 4 volts across here, and our 7 volts is going to stay there. Now let's take a quick look at a graph of how the Zener diode works. I'm going to draw a graph. I'm going to put it up kind of high on the board here. You'll see why in a minute. This is going to be a Zener diode that's forward biased. So we have 0 volts here, and we're going to have 1 volt here. That's going to be 0.5 volts. 1, 2, 3, 4, 6, 7, 8, 9. And then our current is going to be over here. I'm not going to worry about how much current we have exactly, but what's going to happen is, if I draw the circuit over here real quickly, I'm going to put our Zener diode in here, forward biased. And there's our variable resistor, our variable power supply. And as I crank up that voltage, just like any regular diode, we're going to get no current, no current, no current, no current, no current. So as I crank this up from 0 to 0.5 volts, this diode is going to act like pretty much like an open switch, and we're not going to get hardly any current at all. But we're starting at about 0.5 volts, it's going to start to conduct a little bit. And then by the time we get to 0.7 volts, it's going to be conducting a lot of current. So we get this logarithmic curve. And after we pass 0.7 of a volt, it's going to go cascading up, and a tiny increase in voltage is going to give us a tremendous increase in current. And it'll typically be between 0.7 and 0.8 volts, but a big Zener diode, which they do have big Zener diodes, might have more, just like any other diode. So forward biased, our Zener diode just acts like any other silicon diode. But now let's flip this diode around and work it in our circuit the way we expect to use a Zener diode. Reverse bias, so the current's flowing that way, positive on the cathode, negative on the anode. Let's get that out of the way because we need room for our graph. So we're going to go into negative voltages, which will be to the left, and negative current. It simply means the current's going the opposite direction. Get that out of the way here. So there's our negative current, there's our negative voltage. And I will start out with a regular diode real quickly here. So there's 10, 20, 30, 40, 50 volts, let's say. So a regular diode, if we reverse bias it, is just acting like an open switch. We increase the voltage, nothing, no current, no current, no current. Now remember, the current's going to go downward because it's negative current. All that really means is it's flowing the opposite direction. But when we get to the peak inverse voltage, or the breakdown voltage of that small diode, or that regular diode, it's going to suddenly conduct like gangbusters, and it's probably going to burn out unless we have a huge resistor on there to limit the current. It's going to burn out because it's not designed to work there. However, I'm going to zoom in on this a little more. Notice my scales are different. This is 1 volt over here, and I had 50 volts there. Now I'm going to have 1 volt, 2 volts, 3 volts, 4, 5, 6, 7. So there's our 7 volt Zener diode. 1, 2, 3, 4, 5, 6, 7, 8. So there's 5 volts. And the Zener diode is going to act the same way. As we reverse bias it, we get hardly any current, no current, no current, no current. Now at lower voltages, like if we have a Zener diode that's rated at maybe 3 volts, it's going to make kind of a lazy curve as it goes around. And so lower voltage Zener diodes are not really that sharp in their breakdown and in their conductance. It gets kind of a slopey here, so they're not quite that precise. But as we get higher and higher in the breakdown voltage, or the Zener voltage, that gets sharper and sharper. We get up to around 7 volts. It's going to be a lot sharper. Very, very tight turn, and even higher voltages, it's almost like a crease. So it gets a sharp turn and goes much straighter up and down. But remember, it's designed to operate in this region where we get maybe 40 or 50, let's make it 50 like we had before, 50 milliamps. So we want to operate it right about at that current there, so we want to keep it right there. Notice that if the current goes down, the voltage does not change. So voltage changes are left and right. If our current goes down, the voltage is staying pretty much the same. If it goes up, it stays pretty much the same. And it maybe wants to operate in this region. Of course, if it gets up too much current, it's going to exceed its power rating and burn up. But we're not worried about that. We'll just choose a series resistor that keeps the diode within its power rating when it's operating normally. There might be some circuits we'll talk about another day where we have to be more careful about that, but typically we're not going to have to worry about the current changing through the diode that much. We're going to have small fluctuations, and the diode's there just to give us a steady reference in an area where voltages fluctuate. So in a nutshell, what is a Zener diode? It is a variable resistor, which is smart and changes its resistance to whatever it takes to keep this voltage at some rated voltage. Whatever that is, they have many different ratings of Zener diodes. Choose a diode, 6.1 volts seems to stick in my head as a rating I see fairly frequently. So you might find ratings that are right on voltages, but they tend to be fractions of voltages. And here's a data sheet I'll just throw up here. It's a particular series of Zener diodes, and you see you get a 1N. You see they start with the same two digits, and the other two digits are different. And as we go through the series of digits, we get higher and higher voltages, and just choose the diode that you need. So don't forget we got the little green man in there, watching the voltmeter and controlling that resistor to make that resistance whatever it takes to keep that voltage whatever the rated voltage is. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.